All right, well, good morning, everybody. So please don't forget to turn in the homework. Just add yours to the pile that's up here. I've already posted the solutions in the glass case outside my office, as I do every Wednesday. So certainly want to take a look at that. Let me also just remind you that your first midterm exam is coming up, probably sooner than you would like, but it is scheduled for next Friday. So yeah, that's the 27th, right, a week from Friday. And it could cover anything up to chapter 10.3, which is basically the simple Rankine cycle. So this material that we're starting now, dealing with the reheat Rankine cycle and any other variations, will not be on the test, but certainly anything on the Otto and the diesel cycle and the Brayton cycle with all of its variations and different methods of solution could also be on the test. Let me also just let you know well in advance that the format is going to be closed book, closed notes, but you are going to be allowed to bring a 3x5 note card that's inches. And you can write on both sides if you like to. So that's for equations and diagrams only. You're not allowed any sample problems or worked out methods of solution, outline methods of solution, anything like that. It's just so you don't have to memorize all these various equations. So 3x5 inches, one 3x5 card on both sides, or equivalent. I mean, if it's easier for you to just mark out the front and the back of a 3x5 card on a piece of binder paper, then that's fine with me. But let's just call it a total of 30 square inches, any way you choose. But that, and you'll also be given a copy of the property table handout. That is actually shown on Blackboard if you want to just look at that. It's just the appendices from your textbook. So all the appendices that you would need will be provided, and it will also include the various conversion factors that are in the inside back cover of your textbook. So again, this is a week from Friday, and we'll talk next week more. In fact, next Wednesday, I would generally set aside time, really before any midterm, I'll set aside some time just to answer questions and make sure you understand what's going to be on the exam. Nonetheless, you should certainly start thinking about putting your note cards together. So anyway, let's just continue now where we had left off last time. So please keep in mind that the first variation that we're going to look at on our Rankine cycle is that of reheat. What we're going to do here is allow the steam to pass through the turbine, one stage of the turbine until it reaches some prescribed intermediate pressure. And then we're going to reheat at constant pressure up to a new temperature. That temperature may be or may not be the same as the temperature going into the first turbine. Nonetheless, we'll reheat up to another temperature, and then we'll expand down to the pressure of the condenser. So work is actually going to be done in two stages. You've got two turbines, and then we also, of course, would have extra heat input associated with the reheat process, right? So that heat input is also going to have to be included in our various equations. Now, last time we had discussed this, I had set up the general diagrams, the TS as well as the schematic. But now let's just look at the equations. And quite frankly, the important equation is still the thermal efficiency, right? We're still dealing with the heat engine cycle. This is still going to be the net work over the heat input. So please make sure that you're using the right equation here. It could also be shown as 1 minus Q out over Qn, but I generally write it this way. And then also note that the net work is, of course, just the difference between the work required by, the work produced by the turbine less the work required by the pump. And let's also just keep in mind that this isn't really any different than what we already saw with regards to our ideal simple cycle, right? We know that work is just going to equal the enthalpy change for that process, or if it's heat transfer is just going to equal the enthalpy change. So we have the turbine, and again, you'll have to refer to your diagrams and your notes from last time. So we've got our first turbine from 3 to 4, so we have an H3 minus H4 term. Then we have our second turbine after reheat from 5 to 6, so H5 minus H6. So those collectively are the turbine work. And again, I'm writing it all on a per unit mass basis. This is typically how we do this. And then we subtract from that the work required by the pump. which is going to be H2 minus H1. And then, of course, the heat input is going to be in two places as well, right? So after compression by the pump from 2 to 3, we add heat in our boiler. So H3 minus H2. And then we also, after the first turbine, we add heat as we go from 0.4 to 0.5. So we need another term, H5 minus H4. So this then is the overall equation for the thermodynamic efficiency. Okay? And again, it's just going to be in terms of enthalpies. Now, one thing you could do if you really wanted to, certainly we don't have to do this, but we could indeed rearrange this whole equation. We could put an H3 minus H2 term together in the numerator, and an H5 minus an H4 term together in the numerator. And then you'll see that they'll actually combine with the H3 minus H2 plus H5 minus H4 term in the denominator. So if we do that, I'm not going to go through every step here, but nonetheless, the H3 minus H2 plus H5 minus H4, those are going to cancel in the denominator, and that's just going to give us a value of 1. And then all that's left in the numerator is an H6 and an H1 term. So we're going to have minus H1 minus H6. I'm sorry, 6 minus 1. So that's going to be the numerator. And then the denominator is the same as we have above. So there's still an H3 minus H2 minus H5 minus H4. Now really, the only reason I put it in this particular form is just so that we understand that this is indeed equal to 1 minus Q out over Q in, right? Q out is the heat rejected by the condenser as we go from 6 back to 1, and Q in is going to be the combined heat input in the reheater as well as in the boiler. Just a second. So this is Q in. And yes? Oh, yeah, you're right. Thank you. Right. These are additive terms. I'm hoping that the other hands were for the same reason. Okay. So nonetheless, we could use either this equation or this equation. It's going to give you exactly the same results. Okay, now what if we have the non-ideal case? I mean, basically, as this was set up, this was for the ideal Rankine cycle with reheat. If we have the non-ideal case, then like we've seen before, this basically just means that we need to use the isentropic efficiency of the pump and the isentropic efficiency of the turbine, right? In that case, we would have the same methodology as we would have covered previously. We're going to first assume that it's an ideal process, right? We looked at an example problem last time. First, we'll assume it's an ideal process from 1 to 2, and then we find the actual process from 1 to 2. Same thing from 3 to 4 and 5 to 6. Perhaps I should at least show this on a TS diagram. So, we would go from 1 to 2s, and then the actual point 2 will be found using the isentropic efficiencies. We'll add heat until we get to point 3. We're assuming that we have a reheater now, so let's just show an intermediate pressure. So we would expand ideally from 3 to 4s. We apply the isentropic efficiency to get 4a. We reheat up to 0.5. And then we do the same thing. We assume that it's an ideal expansion from 5 to 6s. And then we again use the turbine's isentropic efficiency to get the values at 6a. And then, of course, we would have our heat rejection. So for the non-ideal case, we certainly have a slightly different diagram, but the equations are the same. Except we're simply going to have to replace everything that doesn't have a subscript a with a subscript a, right? So anywhere that you see 2 or a 4 or a 6, we're going to have to substitute in, 6a, 2a, 4a. So same as before, except we use 2a, 4a, and 6a really in place of 2, 4, and 6. So I don't think it really needs any more discussion than just this. What I would like to do, though, is go through an example problem and make sure everybody understands how to solve this particular type of process with reheat. So, well, again, if I were thinking ahead, I probably would have put that so that I could lower the screen without covering it up, but I guess I can't. So do the best I can here. Well, hopefully I can fit all of it on the top there. Okay, it should be coming up shortly. Okay, that looks good. So this is problem 1031, and it's from your current, the 8th edition of the textbook. And here we're told that we have a steam power plant that operates on the, is that the right problem? Yeah, this is the right problem. Okay. Anyway, we have a steam power plant that operates on the ideal reheat Rankine cycle. This is ideal, so I'm not going to use isentropic efficiencies. Whoa, that wasn't supposed to happen. Okay, well, okay. It just says saturation lines down there at the bottom, and unfortunately I can't raise it any higher. All right, so we have a steam power plant. Steam power plants are modeled using the Rankine cycle. In this case, we're told that we have an ideal reheat Rankine cycle. We're given the pressure and temperature as it enters the turbine. And we're also given the pressure as it leaves at 2 megapascal. Note that it does say the high pressure turbine. So these conditions of 6 megapascal and 400 clearly represent 0.3. It leaves at 2 megapascals, so that would be the pressure of the reheat. So we're going to reheat at 2 megapascals from 4 to 5, and it says it's reheated to 400 degrees Celsius, so it turns out that T3 and 5 are the same. And it then finally expands at 20 kilopascals, so that's going to be our pressure, our minimum pressure at 6. And we're just asked to find the turbine work output and the thermal efficiency, and also show this with respect to the saturation lines. Now, let me note that this diagram I put over here is still applicable, although we're not dealing with a non-ideal case, so you should really be looking into your notes from last time, and we're not looking at 2As, 4As, 2S, 4S, et cetera for right now. All right, so let's just indicate what we have. Maybe I'll just do a quick TS diagram relative to the appropriate lines. So 1, 2, 3, 4, 5, and 6. I'm not really sure exactly what my thermodynamic state is leaving the turbines. So often I would just kind of leave off the right-hand side of the saturation lines until we're at the end and then see what's what. By the way, these lines should be horizontal. I clearly didn't do a very good job. All right, so let's just identify what we know and what we don't know. We're given the temperature and pressure at 1. So 6 megapascals, I'm sorry, 3, yeah. Pressure and temperature at 3 are 400 degrees Celsius and 6 megapascals. Let's note that P3 and P2 are the same. They've also told us that it leaves at a pressure of 2 megapascal. So P3 is 2 megapascals. And it tells us that the temperature is the same. Again, we're missing the points here. Okay, time to slow down and breathe. All right, so P4, right, we leave that turbine at 2 megapascals, and then we reheat back up to 0.5. So this is T5. In fact, I really should have shown this a little bit higher, right? Since we're heating back up to the same temperature. All right, so this is P4, but of course it's also equal to P5. And then we're told finally that we go down to 20 kilopascals, so P6, which of course is the same as P1, is 20 kilopascals. So that's the data that we're given. And we want the turbine work output. And we also want the thermal efficiency. Okay. So it's actually straightforward, right? We're given the conditions at point 1. We know that the pressure at 1 is 20, but that it's also a saturated liquid. So we could look up our enthalpy and entropy there. We know that S1 equals S2, but we also know that we have really poor compressed liquid tables in our book. So we don't really need to look up the entropy at point 1. We really should look up the specific volume and then use V delta P in order to find the point 2. So at T1, it's a saturated, at P1, it's a saturated liquid. So we'll be able to find H1 is just HF, and V1 is VF. We'll look those up in a moment. We'll also know that H2 minus H1 is a specific volume times P2 minus P1. So that will allow me to find H2. We're given the pressure and temperature at point 3. So we should be able to go into our appropriate tables and find the enthalpy at point 3. And here, of course, we are going to need the entropy at 3. Now we're going to expand isentropically from 3 to 4. So we know the pressure at 4, and we know that the entropy at 4 is equal to the entropy at 3. So we have those two properties. So then we should be able to find the enthalpy at point 4. Okay. We then go through the reheat process. Again, I'm just going through the methodology first, and the numbers get plugged in later. So we now are also given the conditions at point 5. So at P5 and T5, again, we go into the appropriate table, and we look up the enthalpy and entropy at 5. And then we do the same thing from 5 to 6 as we did from 3 to 4. So now at P6 and S6, which equals S5, well, again, we go into our property tables, and we should be able to find the enthalpy at point 6. Now, we're not likely going to be able to find it directly. It's very likely that point 6 is going to be a two-phase mixture, in which case we'd actually have to use the entropy first to get the quality, and then the quality to get the enthalpy. But nonetheless, at least we can find all of our property data. And then last but not least, it's just a matter of finding all of our work terms. The turbine work output is going to be H3 minus H4. It's H5 minus H6, two turbines. So we have to include both of them so we can calculate that. And of course, to find the thermal efficiency, we're also going to need the heat input. So H3 minus H2 plus H5 minus H4. So we'll calculate the heat input. And of course, we're also going to need the network to find the thermal efficiency. So that'll just be the turbine minus the pump work. And the pump work is just going to be H2 minus H1, which you already have over here. So you can even go ahead and add that this is equal to the pump work. Okay. So now it's just a matter of going through the math, right? So we're going to start with state point 1. We're given the pressure. We know that it's a saturated liquid. That means we go into our saturation pressure table, which is table A5. And then we move forward. We just look up the value of enthalpy and specific volume. So we have 251.42 kilojoules per kilogram for the enthalpy, and for the specific volume is 0.001017 cubic meters per kilogram. We can now plug this in below. And the pressure difference from 1 to 2 is between 20 and 6,000. Certainly we need to make sure everything's in kilopascals. And of course, the kilopascals are kilonewtons per square meter, et cetera, et cetera. The units cancel. We've seen this before. And this just gets us into kilojoules per kilogram. so no conversion factor is necessary. This is 6.08. Okay. In fact, we don't really need H2, at least not at this point, but we can still find it. We will need it later as we look at our heat input terms, right? So let's just also note, therefore, that H2 is just H1 plus the pump work, and that gives us 257.50 kilojoules per kilogram. All right, so that's done. Now we start with the turbines. This is very similar to what we did last time as well. So at P3 and T3, this is clearly going to be superheated. So we go into table A6. We go to the 6 megapascal subtable. We read down to the 400 degrees Celsius line. We move across and just read the data. So 3178.3 kilojoules per kilogram is the enthalpy, and 6.5432 kilojoules per kilogram per Kelvin is the entropy. And now we have to move on, and we would note that S3 equals S4, and we know P4. It turns out that this is also superheated. We can make a pretty easy and quick check, right? We could just go into our property table at P4 and compare the value of entropy to SG. And it turns out that the entropy at 0.4 is greater than SG, right? The entropy of a saturated vapor at that given pressure. So it's to the right of the dome, right of the saturation curves if you prefer, and superheated. So go to A6. Now we know the pressure at 4, that's 2 megapascals. We just read down to the appropriate value of entropy, and we are going to have to interpolate in order to find the enthalpy. But in doing so, we would get H4 of 2901.0 kilojoules per kilogram. And now we move on to 0.5. So again, we know the temperature at 0.5, we know the pressure at 0.5. Clearly, if 0.4 is superheated, then 5 has to be even more superheated since we're adding more heat to it. So we don't have to make any tests, we just know. So we go into table A6 and we read off the appropriate enthalpy. So that's 3248.4 kilojoules per kilogram and 7.1292 kilojoules per kilogram per Kelvin. Okay, and now we do the same thing as we did before. We're going from 5 to 6 instead of 3 to 4. Probably the biggest difference is that indeed we will find that 0.6 is a two-phase mixture. We will go into table A5 down to the 20 kilopascal line. And again, we're just going to compare the entropy to SG. And in this case, S6 is less than SG. So we're inside the saturation region, and it's a two-phase mixture. So we can't find the enthalpy directly. We have to use entropy to get the quality, and then use that quality to get the enthalpy. So just plugging in the numbers, S6 we know, 7.1292. SF is 0.8320. SFG is 7.0752. And this allows us to find the quality, and it's 0.890. And then we use it to find enthalpy. So again, just pull the numbers out of the table. 251.42 is HF. And HFG is 2357.5. And this leaves us with leaves us with 2349.7 kilojoules per kilogram. All right, so now we have all of our enthalpy data, and I suppose I could now finish up the TS diagram. If 0.6 is clearly a two-phase mixture, then this figure is very much out of scale. I'm just going to totally redo the right-hand side of it. make my dome a little bigger perhaps. And try to make these a little more parallel. All right, so 3, 4, 5. How about that? And 6. So a little more accurate anyway. Nonetheless, I'm not going to bother to plug in the numbers here. We have all the enthalpy data. We can find all these terms. The turbine work output is 1176 kilojoules per kilogram. The heat input is 3268 kilojoules per kilogram. The net work is 1170 kilojoules per kilogram. And finally then, the thermodynamic efficiency, which is a net work over the heat input, is just 0.358. Or 35.8%. So there you have another problem that is specifically the Rankine cycle, but the ideal Rankine cycle with reheat. Now, if we were to want to do the same problem, I'm not going to do this, but if we had the same problem but with a non-ideal turbine and pump, it doesn't change things a lot, right? I mentioned briefly before what we do, but let's just talk about it briefly again. Here, this term would not be H2, we'd call it H2S, right? And then we'd apply the isentropic efficiency, which is H2S minus H1 over H2 actual minus H1, and that gives us H2 actual. So that part's done, and we do much the same for the first turbine. This value of H3 is going to be found with the appropriate entropy. When we go from 3 to 4, we get H4, but now it's going to be called H4S, right? We assume it's isentropic from 3 to 4, S. And then we use a turbine's isentropic efficiency, H4 actual minus, H3 minus H4 actual over H3 minus H4 ideal. And that's going to allow us to find H4 actual. And we do exactly the same thing from 5 to 6. Of course, this is going to be H5, but this is going to be H6S. And then we find H6 actual from H6S using the isentropic efficiency. And again, just replace the 2, 4, and 6s with 2A, 4A, and 6A, and you'll get the results. Okay. I would note, though, that if we have a non-ideal set of turbines and pump, then things are definitely going to change, right? The points 2 and 4 are going to be different. The net work output is definitely going to be less because we're losing some work due to the inefficiency of the turbine and the pump. So we'll end up with a lower thermodynamic efficiency. Anyway, any questions on this one? Good. Which now allows us to move on to the next variation of the cycle. Okay. So this next variation is what we call the regenerative Rankine cycle. Now, when we talk about the regenerative Rankine cycle, we're talking about the need for the use of regeneration. And I believe I mentioned this last time, but regeneration in the context of a steam power plant, a Rankine cycle, is different than that associated with a gas turbine power plant, a Brayton cycle. Okay? We saw that in the Brayton cycle, the discharge from the turbine was at a high enough temperature, we could just send that exhaust gas, if you will. Of course, it's air in our cycle, but we would just send that to a heat exchanger that we call a regenerator and just transfer heat from that high temperature gas leaving the turbine to the lower temperature gas, which of course is air, leaving the compressor before it goes into the combustion chamber. But that was for the Brayton cycle. We've now seen several TS diagrams, and it should be pretty clear that we can't do that anymore. The temperature as we leave the turbine is going to be very low. The temperature leaving the pump is going to be considerably higher, so there's no way to exchange heat from something cooler to something warmer, right? We need to exchange heat from the warm thing to the cool thing. So we can't use regeneration in the same way. But we can still talk about a regenerative Rankine cycle. One thing that could be done as we start this discussion is to just look at what's happening during a portion of the cycle. And let's just look at the TS diagram during the compression process. So we're going to start at point 1. We'll pump to the higher pressure up to point 2, and then eventually we're going to add heat until we get up to some point 3. Okay, so this we know. One thing that we might also remember or also know is that we're trying to maximize the thermodynamic efficiency, and one way to maximize the thermodynamic efficiency is to maximize the temperature at which heat input takes place. Now, you can see that in a typical cycle, a typical Rankine cycle without regeneration, we're going to pump up to the high pressure of the boiler, but that temperature is still going to be considerably less than the saturation temperature associated with that pressure, right? It's also still going to be quite a bit less than T3. So the average temperature during the heat addition process is somewhat depressed from the saturation temperature just because of the nature of the compressed water at point 2. So what we're really trying to do when we talk about regeneration here is we're still trying to preheat our water before it goes into our boiler, before it goes into our heat input device. So that's really the same as we're trying to do for the Brayton cycle. We're still trying to preheat, but we just can't do it quite in the same way. And by preheating the water, the average temperature at which heat is then added from our external source, which of course is the only heat input term in our thermal efficiency equation, that heat input should become a little bit lower as the average temperature of the heat input process rises. So that's really what we're trying to do. So we try to increase the average temperature during heat input, and this should increase the thermodynamic efficiency. So the question now becomes, well, how exactly do we do that? It's not clear yet. So let's talk about that. So let's first look at a regenerator that we typically don't use anywhere, and we'll just call this, how would we call this, an ideal regeneration process. Okay. So let's show this on a schematic diagram as well as a TS diagram. So let's say that here's my pump as I go from point 1 to point 2. And let's over here show the condenser. Coming into the condenser will be a point 6, although we're not sure really where that comes from yet. And then there's going to be a turbine up here somewhere. And the discharge from this turbine is 0.6. Okay. And now let's look at the regeneration process. So you'll see that eventually when we expand through the turbine, eventually the temperature is going to be quite a bit lower. But where the steam goes into the turbine, the temperature is actually pretty high, and it's even higher than the temperature we have at point 2. So what is proposed here is to actually exchange some heat from the steam that's moving through the turbine with the water that's leaving the pump. So from point 2, we're actually going to come over here to the turbine and essentially wrap a big set of coils around the outside of the turbine. And since what's going through the turbine is warmer than state point 2, by wrapping these heat exchanger coils around the turbine case, you're actually going to increase the temperature. So we're going to come out here at point 3. And now I should show the boiler. So over here, I'll have my boiler. So what comes out of the boiler is going to be point 4. And now this steam is actually going to go into the turbine. So please don't confuse the windings that I've shown around the outside of the turbine with the steam that's flowing on the inside of the turbine. So the steam's going into the turbine, and as it moves through the turbine, it's giving up some of its heat. At some intermediate point, actually at the point where the water comes in out of that pump, that point we're going to call state point 5. And then the steam's just going to continue through, doing a little more work until it finally leaves at point 6. So this is what an ideal regenerator would look like. And to show this on a TS diagram, we would basically have the following. So here's our saturation lines. Let's just show our minimum and maximum pressure lines. So we're going to start here at point 1, and we're going to compress up to point 2. And then what leaves the turbine is going to be, what enters the turbine is going to be over here at point 4 somewhere. So as the steam starts passing through the turbine, at first it's just going to be an isentropic process, but eventually it's going to start to see the tubes, the windings, if you will, on the outside of the turbine. So at this point, the temperature is going to start to drop even more, and it's not going to be isentropic anymore. So we still have isentropic expansion through the turbine, but we also have heat exchange taking place. So we're going to actually start moving kind of at an angle. We're going to de-superheat right away, and then as we continue to exchange heat, eventually we're going to end up in the two-phase region. And then eventually we're going to get here to point 5, and that's where the windings end. And now the steam is just going to continue its isentropic expansion until we get to point 6. On the water side, as we leave the pump here at point 2, we're going to start picking up heat. So we're going to rise like this until eventually we get up to some higher temperature at point 3. Okay. And then we're just going to continue with the heat input process from the boiler, and that's what our cycle would look like, something like that. Yes? So at point 3, our stage is still compressed liquid? It's still compressed liquid, although I might note that it really depends entirely on the process. I mean, it depends how much heat is transferred. It is possible for this to get into the two-phase region. Here I've just shown it as being saturated or compressed. But yeah, it doesn't really matter. And the same thing goes with state point 4 over here, right? There's nothing that says that 4 has to be superheated. 4 could be saturated, it could be two-phase. So the shape of this curve might be a little bit different, but at least the general process is accurate, right? We're pumping up to point 2. We're then taking some of the heat out of the turbine to preheat the water. And then when we add heat in the cycle, the heat input process is only between point 3 and point 4. Okay. Keep in mind that this is another one of those internal heat transfers. When we looked at regeneration for the Brayton cycle, we recognized that the amount of heat gained by one stream is equal and opposite to the heat lost by the other stream, and in a thermodynamic sense, it's a complete wash, so we don't end up with any net heat transfer, right? We also know that our thermal efficiency is only a function of the heat input from external sources, so here we have a lesser amount of heat input. And again, with lower heat input, we should improve the thermodynamic efficiency. Now, all this sounds good in principle or in theory. The problem is that it's simply not practical. Okay, there's a variety of reasons that it's not practical. The one that, at least in my mind, is the biggest problem is simply the turbine casing / heat exchanger design. Keep in mind that the casing, which holds the turbine blades in place, is a big, heavy piece of metal. To turn that into a heat exchanger, to somehow introduce heat exchange tubes within this casing would be an incredibly difficult task. Okay? You have got very high pressure moving through that turbine. If you start messing with the turbine casing for heat transfer purposes, you could very easily weaken it, and the design would just explode. It would just break itself apart. Or if you had to make it thicker because of all the tubes and the interference with those tubes, then it might be just really expensive and not worth it. But nonetheless, the casing / heat exchange design, basically all this is extremely difficult. Is there a question?
I was going to ask, because you want your turbines to be like adiabatic, right, for the max possible efficiency, or as insulated as possible, so that
Right.
coil would have to be inside the turbine?
Well, basically, it would have to at least have the ability to transfer heat. So I suppose you could have the moving blades and then have some inner casing with the heat exchange surfaces and then an outer casing. But still, it becomes problematic to do the design. Another thing that should be noted is that steam is a very poor heat transfer medium. And we're definitely, in this particular case, exchanging heat from steam. Now keep in mind that steam is a gas, right? And gases have a very low density. So to get any appreciable amount of heat transfer from a low density fluid, you need to have very large surface areas. So not only is it going to be hard designing it, but the physical area required to transfer heat from that steam may not even be sufficient. So the fact that steam is a poor heat transfer medium becomes another problem. A third issue has to do with the state of the steam as it leaves the turbine. And we'll note that the steam is a two-phase mix as it leaves the turbine. And we really don't want that, okay? In fact, maybe I shouldn't even say as it leaves the turbine. I should probably say it's a two-phase mix during the last half to two-thirds of its travels through the turbine. So steam is a two-phase mix through much of the turbine. Now, why is that a problem? Well, it has to do with erosion. Steam turbine blades are spinning incredibly fast, right? They spin at whatever the speed of the electric generator is, which is usually 3,600 RPM or 60 revolutions per second. If you have steam, which is a gas moving through those blades, not much potential for erosion. Well, it's a gas, right? Very low density. But liquid water has a density of 500, 1,000 times that of the steam. So any water droplets, any of the liquid in the two-phase mixture is going to definitely cause erosion on the turbine blades. So there's another reason why we really don't want to do it this way. We don't want erosion of our turbine blades. We really like to keep the steam moving at least as long as possible through the superheat region so that we don't have any liquid, so we don't have erosion problems. So what do we do then? We would like to use regeneration, but the true regenerator, this ideal regenerator, is not particularly practical, so what can we do? Well, what we do is called feedwater heating. We use feedwater heaters. Okay? And basically, we're essentially mimicking what's going on here, but rather than actually having a heat exchange process, we're actually going to draw some steam off of the turbine at some intermediate point. We're going to extract that steam, if you will, and we're going to actually either mix it directly with the liquid moving through one of these pumps or moving through this pump, or we'll go through a heat exchange process between the extracted steam and the pump. So we're going to use feedwater heaters. We actually extract steam from an intermediate part of the turbine and transfer its heat to water leaving the pump. Right? So this is what can be done. And there's actually two different ways to do this. One way is through a device called a closed feedwater heater, and the other is through a device called an open feedwater heater. So basically there's two types of feedwater heaters. And I'm just going to abbreviate feedwater heater as FWH, so I don't have to keep writing feedwater heaters over and over and over. But there's two types of feedwater heaters. One is called a closed feedwater heater. And in a closed feedwater heater, this is where we do not have any mixing. This is where we're going to actually take that steam and run it through a separate heat exchanger with the water. So the closed feedwater heater is actually a heat exchanger between steam. In fact, let me call this extraction steam. That's the steam we're extracting. So between the extraction steam and the water. And the other possibility is what we call an open feedwater heater. In an open feedwater heater, we don't have a heat exchanger. We physically mix together the two streams. And in mixing together those two streams, the warmer, higher energetic steam heats up the water. So we mix together the extraction steam and water. Now you may ask, why do we even call this a feedwater heater? I think we understand why we call it a heater, and even the word water makes sense, but why feedwater? Keep in mind that this water is being fed into the boiler. So we call it feedwater. The water feed into the boiler. The pump we often call a feedwater pump. If you go out in industry, this is the terminology you'll see. So the water is fed into the boiler. We call it feedwater. We're heating up that water. We call it a feedwater heater. Okay. So with all this in mind then, let's note a few things. The first thing I want to note is that we're not going to cover closed feedwater heaters in this class. Okay? If you're interested in closed feedwater heaters, then take ME 411, or it'll be 4110 starting next fall, and there we go into a lot more detail as to the nature of closed feedwater heaters. But in this class, we're going to ignore them entirely. So, not covered. That doesn't mean they're not important. In fact, what you'll find is that in the real world, most feedwater heaters are indeed closed feedwater heaters. You'll typically have one open feedwater heater at the steam power plant, and the number of closed feedwater heaters is large. There's not just going to be one extraction steam line going to a single feedwater heater. You'll easily have 6, 8, 10, a dozen feedwater heaters. You'll be drawing off steam at multiple intermediate points, running to multiple feedwater heaters, and actually heating up the feedwater in very many small stages. This allows us to maximize the efficiency. Again, this is something we're not going to talk about in this class. Okay? In this class, not only are we going to avoid talking about closed feedwater heaters and only deal with open feedwater heaters, but also in this class, only one feedwater heater will be assumed to exist. Okay. Again, in reality, there's going to be multiple feedwater heaters, and we just don't have the time to go through that in this class. Okay. So what would the cycle look like? What would it look like from a TS diagram point of view? What would it look like from a schematic point of view? In fact, even before I get into that, let me make one other comment about the open feedwater heaters. They really serve two purposes, one of which has absolutely nothing to do with the thermodynamics, but is incredibly important, and it actually has to do with the quality of the water. And I'm not talking about quality in the context of liquid versus vapor. I'm talking about the purity of the water. And it's not minerals that I'm worried about, it's air that I'm worried about. Okay? When you have water, water being a liquid, all liquids have the ability to contain, or if you will, have a certain amount of gas absorbed into them. Any water that exists in the environment will actually have some air saturated within that liquid water. This is something you know sometimes when you turn on your water faucet, you relieve the pressure as it hits the cup, and the water starts getting all fizzy. Well, where did that fizziness come from? Well, that's just air that was previously dissolved in the water, and the water in the pipes is at what, 100, 150 psi, but when it goes into your kitchen, it's at atmospheric pressure. Lower pressure water can't hold as much gas, so the gas comes out of solution. So it's air that becomes a problem. Any air that exists within our water streams will cause at least the potential for corrosion issues, right? Air will oxidize metals. So you have corrosion issues, you have the potential for explosive mixtures. You don't want any air dissolved into that water. So the open feed water heater will actually take care of that for you. Yes, it is a heat exchanger, but it's a mixing process, and through the turbulent mixing of steam and liquid water, air that's actually dissolved in the water will come out of solution. So you're always going to have one open feed water heater, and often it's just called a deaerator. I mean, I've gone to plenty of power plants where they don't even use the word feed water heater. They just continually call it a deaerator, which is fine. From an operational point of view, that's what they really want. They're concerned about water quality. So the open feed water heater is a deaerator. It's important. Closed feed water heaters are actually cheaper than open feed water heaters, and that's why you find so many closed feed water heaters in existence. And as such, you really only need the open feed water heater, not even for feed water purposes, although it helps, but also, again, for deaeration purposes. Nonetheless, that's a side point. We're only interested in the thermodynamics. So again, what does it look like? So let's just start with, I don't know where I should start. I guess at a pump. Okay. So here's our pump. And I'm just going to call it a feed water pump. So we're going to enter this pump at state point 1. And the first thing that we're going to do is actually go into the open feed water heater. So we're going to leave it 2, and here is the open feed water heater. So open feed water heater. And the open feed water heater is really just a big mixing chamber. If you want to know what type of equation we're going to use for its analysis, it's just a mixing chamber. We've got 2 fluids coming in and 1 fluid going out. So you might want to note somewhere that it is a mixing chamber. And you can go back to chapter, 5, and look up all the different types of devices that we use single stream steady flow or multiple stream steady flow analysis on for open systems, and it's just a mixing chamber. All right, so we have our open feed water heater. The water comes in at point 2, but also there's going to be the extraction steam that's extracted from the turbine, and we'll get to that in a moment. Now, the nature of open feed water heaters is very much like the nature of condensers. In essence, we're always going to have a 2-phase mixture within here. This part's liquid, this part's steam, but the mixture is going to be a 2-phase mixture. And it's at the very bottom of the feed water heater where you just have the saturated liquid that you're actually going to draw that liquid off and send it up towards the boiler. So please note that since this is an open feed water heater, and since the extraction steam is coming in at some intermediate pressure, this pressure is not the same as the boiler pressure. This is an intermediate pressure. This will be more clear when I put the TS diagram on the board. But nonetheless, the open feed water heater requires another pump. So we have another feed water pump, numbers 1 and 2, I suppose, and leaving this feed water heater and leaving this pump, we're at state points 3 and then 4. Okay. And now we go to our boiler. So we come out of the boiler at 5. And now we go into our turbine. So we have steam passing through the turbine. And it's at some intermediate point that I'm going to call 6 that we're going to draw off the extraction steam. And then the remaining steam that's in that turbine is just going to continue until it finally gets to the pressure of the condenser. So this is at point 7. And here's my condenser. And we have our saturated liquid that gets pumped right back into that open feed water heater. All right, so this is the basic process. Please note that the pressure of the feed water entering the feed water heater and the pressure of the extraction steam have to be the same. Okay, if they're not the same, then you have flow problems, right? If the steam pressure is greater than the feedwater pressure, then steam's just going to start to shoot down and backwards into your pump and backwards into your condenser. You certainly don't want that to happen. Of course, if the pressure of the feedwater pump at point 2 is higher than the extraction steam pressure, well, again, it won't work, right? The liquid is just going to shoot up this lower pressure steam line and start squirting into the turbine. So you can't have different pressures. So please note that P2 has to equal P6. And since those two pressures are the same as they mix in the open feedwater heater, then the whole feedwater heater is at the same pressure. That also has to equal the pressure at point 3. So all those pressures are the same. And as far as the other pressures in the cycle, I mean, we just know things, right? We know P1 and P7 are the same because we know that heat rejection takes place at constant pressure. We also know that P4 and P5 are the same. Again, we know that heat input takes place at constant pressure. We also know that we've got two sections of the turbine that have to be dealt with. So there's our turbine work output. And of course, there's two pump work inputs, which I'll just call pump 1 and pump 2. Now, let me note something about the turbine here, and still haven't shown the TS diagram. As we look at the turbine, another thing to note is that the flow rate is different between points 5 and 6 compared to points 6 to 7. Okay? So we have to be really careful when we do our thermodynamic cycle analysis. If we've got a different amount of mass flowing through each section of the turbine, then we can't do our analysis on a per unit mass basis anymore. Remember, everything we've done up until now, we've used lowercase q, lowercase w, enthalpies, really specific enthalpies, right, lowercase h. We're going to have to be careful now because we know that the units of mass are going to change. We've got more mass from 5 to 6 compared to 6 to 7, so we have to be really careful with that. Okay. So another thing to note is that the mass flow rate varies. The mass flow rate as we go from 5 to 6 is certainly going to be different, and in fact less than the mass flow rate as we go from 6 to 7. So again, we have to be careful with this, and we have to figure out how to analyze the cycle properly. Now, what does this look like on the schematic diagram? On the TS diagram. Oh, I'm sorry, one more thing before I move on. Sometimes when you see this part of the cycle, instead of a single turbine where we have a single flow path and then we draw off extraction steam in the middle, very often we see this written as if there were two separate turbines. So this whole thing, if you wanted to, it's really up to you, but we could show this as if it were two turbines where we're going to come into one of the turbines at point 5. We'll leave that turbine here at point 6, at which point we're going to draw off the extraction steam. And then we'll continue into the second turbine. Work will be done in that turbine, and we'll come out of that turbine at point 7. Okay, so whether you show it this way with two separate turbines or that way, it really doesn't matter. Remember that one of the things we've talked about is that we're always going to neglect any losses as we exit one device, but before we enter the next device. Okay? So it doesn't matter if we're talking about the Brayton cycle. What leaves the compressor is going to have the same properties as the inlet to the combustion chamber. What leaves the combustion chamber will have the same properties as the inlet to the turbine. The same thing happens here. Okay? As we leave one turbine, we're assuming there's no losses, and what leaves the one turbine is going to be exactly the same as the inlet to the other turbine. So whether I show it this way as if there were two separate turbines, or whether I show it this way with just a single intermediate point, you get exactly the same results. So it's just a different way of thinking about the problem. Again, it's up to you as to which way you want to think about it, but these are identical. So again, same. So finally, on to the TS diagram. So as usual, we should show this relative to the saturation lines. And we are going to have to show 3 constant pressure lines, right? We have one constant pressure line which represents the minimum, which is our, condenser pressure. we've got one maximum pressure line that represents the maximum, in other words, the boiler pressure. And then this is going to be the intermediate pressure associated with the feed water heater. So what do we have? So we start at point 1. Again, 1 is always a saturated liquid leaving the condenser. We compress to point 2. In fact, I should note this is ideal. I'm not going to yet show how we deal with isentropic efficiencies. So we go from 1 to 2. We then have the heat transfer process within the open feed water heater, and at this constant pressure, we will end with point 3. And we leave at point 3, and then we pump up to point 4. And now we add more heat in the boiler until we get to point 5. We now expand through the turbine, and at some intermediate point, 6, this is where we're going to draw off the extraction steam. And the remaining steam continues through the turbine until we get to point 7. Now, again, like all cycles, I don't know exactly where points 4, 5, and 6 are. I've shown these as if 5 and 6 are superheated and 7 is two-phase, but well, we don't know that for sure, right? It just depends on the individual problem. 5, 6, and 7 could all be two-phase. They could all be superheated. It really doesn't matter. At least from an analytical point of view, it doesn't matter at all. But what I should also show on these diagrams is how the flow rates vary from point to point. So if we just let m dot be equal to, let's just call it the full flow rate, and m dot ES, ES stands for extraction steam. So this is the extraction steam flow rate. These are both mass flow rates. Then let's show these on the diagram just to make sure we understand that we don't have the same flow rate everywhere. We have the full flow rate here at point 3. After all, the extraction steam has been recombined with the feed water, so we have the full flow rate. We have the same full flow rate at 4, we have the same full flow rate at 5, and the same full flow rate m dot in that first half of the turbine. But now we're drawing off the extraction steam. So what remains from point 6 to 7 to 1 all the way back to 2 is just that fraction. So we have m dot minus m dot extraction steam. Okay, it's the same throughout all the way until we get to point 2. So we've got a different flow rate in different portions of the cycle. This can also be illustrated on this diagram, right? We have the full flow rate from 3 to 4 to 5 to 6. But then we draw off the extraction steam. So what remains after point 6 is just m dot minus the extraction steam. Okay, and again, it goes all the way up here to point 2. Okay, this is a little sloppy. So this is really all the time I have for today. I've just introduced you to the idea of feed water heaters and specifically the open feed water heater. I think over the next couple of days you should review this material, make sure you understand the basic concepts in the textbook, and then next time we'll finish this all up and I'll end with a nice long example problem that ties everything together. So that's all the time we have for today. Please don't forget to turn in your homework. Just add it to the pile up here. Solutions are already posted. And remember again, your midterm is next Friday. Closed book, closed notes, but you'll be allowed to use a 3x5 note card with equations only and diagrams written on both sides if you choose. We'll talk more about this next week. So see you all Friday.